topic. I'm not going to talk about how to analyze programs or automatically solving programming problems. I'm going to talk about programming problems that arise when you're writing tools to solve programming problems. I'm going to talk about programs that help write programs that help write programs. So this sounds fairly obscure, but I actually became interested in it in a fairly mundane way. It was 2011, my junior year of college, and I was taking a compilers course. And I was finding that every time I wanted to do something, like get a list of all declared variables, I would have to write these giant interversals for I'd look through all the different kinds of statements, and then for each one I'd go in, all different kinds of expressions, I'd go through all the functions, all this code, and then finally at the end, I'd get to the variable declarations, and there I do my real work. So I'm thinking, there has to be a better way. So I look at the implementations of a few other things, and I see that a lot of them are slightly less stupid than me. They write a few traversals and then try to reuse them as much as possible and hope that all the traversals are the same. But even one traversal is pretty bad when you're traversing your lane for 1,000 cases. And also around this time, I was talking about wanting to automatically solve programming problems, like just write one tool and use it in every language. And then someone said to me, you may think C and Java look pretty similar, but really, if you want a tool from them both, you have to rewrite it from scratch. So I've done a lot of reading, and the good news is it is possible to do this. It is possible to write an operation once and use it on many languages. It is possible, with the things I'm going to show you today, to get away with writing 0 traversals, period. The bad news is that you have to do things from the ground up very differently than you would normally. This is not something that you can just add in after the fact.
So I might be jumping the gun here with this question.
Yeah.
But so I know all this is in the context of a startup company.
No.
Or is it?
No. I'm about to draw an example from a real tool, but so I don't know quite what I'm going to get to. So I'm going to have some spiel at the end about how this is really important because of economics, but
so you didn't try to have a profitable company based on writing compilers, right?
No.
Okay, good.
I didn't try to have a profitable company based on writing program repair tools. I was working on a system similar to GenProg. And instead of talking about what it actually does, I'm going to talk about this little operation way deep inside the implementation and beat upon them there. So I'm going to talk about how to replace one statement in a program with another. And so I guess I can keep it here. Okay, so let's hope it stays down. So this is the GenProg way of doing it. It's based on the C intermediate language, CIL, and uses a visitor pattern. It has some general visit function. It says, here's what it means to visit a statement. It's going to do replace. So this is 24 lines of code. The actual traversal that calls this is itself this 500-line function, which goes through all the cases in the C language. And of course, it depends on the rest of CIL. All right, does anyone know how to make the thing not come up?
Stop moving your cursor.
I'm not moving the cursor. Yeah, like every time we change the slide, that reappears.
If they move down, do it.
If I get it to stay around long enough, it's like a Heisen bug. When I want to touch it, it's not there. When I want to hide, it is. So I'm just going to keep going. So depending on CIL, which is of course over 50,000 lines. So this is my way of doing the same thing. It is 6 lines. And I suppose, to be fair, I should also bring in my own language-specific infrastructure, which is 2 lines. But one of those lines is long. And then this all depends on 300 lines, which is fewer than 500, of very generic machinery. And not only that, but the gen prog thing is very much built for C. You have no shot at making it run in Python without rewriting from scratch. For my way, the only thing you do if you want to make this run in Python is you go over there where it says Java prog, you just define a new type for Python programs, and you just change the type signature, and it generates different code.
Do you expect us to read this code? Well, it's completely unreadable.
Yeah, so I unfortunately did. So actually, I intended to print out all the slides beforehand, so I wouldn't care whether or not. Well, I didn't get to test on this projector. I thought I'd print out my slides, so I didn't have to care.
Are these pictures? Did you crop pictures and put them in, or?
Yes.
Yeah, that's why they don't look so good.
Okay, so the resolution on here is low.
Well, we'll talk about it some time. There's some ways you can do it, which is easier.
Okay. So, yeah, so luckily, so being able to read this code is an added bonus. We can take my word for it that where I'm pointing is something that says Java prog. You've just changed that. And I'm going to tell you to change that, it will generate different code that can run in Python. And actually, yeah?
When you say replace a statement, is this something like find all of the x equals y plus 1 and replace it by if z blah blah blah?
Yeah, good point. I should have clarified. So it could be that, and this example would look pretty similar. What this actual example is every statement is labeled. So the arguments are the program plus 2 labels, the source and the destination. And basically, I'm going to find the destination label, find the statements there, and replace it with a copy of the statements from the source.
The different variables could be in scope, right?
Yes. So there is an earlier pass which compares.
Some specific language what you're trying to do.
What?
Take some specific language and tell us what does replace a statement mean. I don't understand what that means. I mean, is it a text editing operation?
No. So this is an operation on syntax trees. So if I have a statement somewhere in my syntax which says x equals 5, and I have another statement somewhere else in my program which is a while loop, then I replace x equals 5 with a copy of that while loop, and that's replacing a statement.
So this is part of a bigger algorithm that does mutation on programs in order to search for a program that will satisfy some particular set of tests. So it goes in and it makes random changes to, well, not completely random, but it makes directly changes to the program.
I'm not going to be able to hold myself.
More than the text part, I understand.
It's simply taking an existing program and trying to make repairs to it.
Okay.
And it's trying to make repairs by finding other locations in that program that might look like if you take the code from that other part and put it here, maybe things will work correctly. So this is part of a repair algorithm. Incidentally, it doesn't work very well.
But it's not.
It's good at removing things.
Yes. That's orthogonal to the talk.
Does the substitution respect typing or scoping?
And that's all. So you can add all kinds of constraints as far as which statements you pick, and then that's a separate topic. So now suppose I wanted to have a replace expression operation instead of replace statements. So with the visitor pattern way, this is very heavily tied to the idea of a statement. Like it's overriding a specific replace statements method or a visit statements method. With my way, you could turn this into replace expression statements, and you actually don't need to change this code at all. The only thing that makes this be statements instead of expressions is that over here there's this lookup statements method there's a map of labeled statements, and it looks up the statements in that map. If you just change the type of that thing and don't touch this code at all, then this will magically instead generate code to replace expressions. Stelios?
Do you think this is an artifact of just using the wrong tool? Like for doing transformations on C code and general other languages, I use TXL, which is a transformation tool that allows you to sort of do the same kind of reasoning that you're doing over there instead of writing passes that you do.
So TXL is actually related to some of the things that I'll talk about later.
But at a high level, is it the same? So if you use TXL, basically you can do what you do on the right.
Yeah. So I'm not familiar with TXL. So let's see. So TXL gets you part of the way.
Mm-hmm.
Let's see. So I'm thinking a bit more about TXL to see what it gives you and what it's not.
Mm-hmm.
But some of the ideas are there, such as more generic traversals.
Yeah, exactly.
Some of the things, such as doing that while retaining type safety, and being able to properly work with different fragments. A lot of those ideas are not in TXL.
The type safety is.
Okay. Well, then I'm wrong. And also later I'll show you strategic programming, different ways of combining traversals, which is something that TXL very much lacks.
Yeah. Okay. Fair enough. Okay.
Okay. So, if you're defining program transformations, you might start off saying, I need a type for program transformation. So how about program arrow program? And if you do that, then you're screwed before you've written any code whatsoever. If you do that, you will, down the line, have to have terrible, unmaintainable, unmodular code. The reason is to think back to the basic subtyping rules from type theory. So, for a moment, I'd like you to think of a subtype as adding stuff to a type. So what this rule here is saying is that if you have a type program arrow blank, then that will continue to work if you take stuff away from your program type, like if you compile away all your for loops. And if you have a type blank arrow program, that can continue to work if you add stuff. It's like you add if statements to a language that didn't have them. But when you have program arrow program, any change that you make to your program type, your code will break, and you'll have to change it. So I have here a data type declaration for a simple expression language with addition, multiplication, and integer constants. And when you write things out this normal way, recursively, you see that the data type informs this graph. And you'll see when you're trying to evaluate this, you will have to both produce and consume values of this expression type. Things are recursive and entangled. And because of that, you're basically going to have to write things of type exp, arrow exp. And you're already screwed even before you get that far. So what we're running into is what Philip Wadler calls the expression problem. Basically, there's two big dimensions in defining language. There are adding new cases, new pieces of syntax, and adding new operations. And it turns out that it's very hard in order to be able to do both without changing your code. So in the previous slide, Adam?
But it's trivial logic programming, right?
Being able to do both?
Yeah.
So I actually haven't seen it. So I know there's a big family of approaches to this problem. I'm only familiar with a handful of them. So with logic programming, I can kind of see some ways of doing that, and a lot of them arguably violate either the type safety or the recompiling code one.
Oh, yeah. Recompiling code, it isn't an important cost anymore, but I can understand it as a constraint if you decide to use one.
Yeah, and you can argue whether that should be part of the definition or not. So on the previous slide, I was using an algebraic data type for my language, and that makes easy to add. And it makes it easy to add new operations. If I add any new cases, then I'll have to change all of them. There's a famous essay by William Cook where he says that this is basically one of the big differences between algebraic data types and objects. With objects, it's the other way around. It's easy to add new cases. It's easy to add new operations with objects if you have everything defined through an interface. It's easy to add new operations if you have everything defined through an interface, but it's harder to add new cases. Well, it's hard to add new operations. So. All right, hopefully that was my bungle for the talk. So I'm going to spend the first part of the talk basically talking about how the modular representations, things that give you both kinds of modularity, and can let you represent terms in every language or without losing type safety and making it easier to add new things. And then I'll talk about the things that TXL doesn't do for you, as far as ways of taking pieces of operations and combining them so that you can start doing awesome things with one-liners. And then I'm going to put them together. So, modular representation. So I'm going to start off in this famous paper by Weierstraße called Data Types a la carte. This big idea in here is that earlier when I had that algebraic data type, the problems came from that cycle. And so now I'm going to break the cycle. There's this general idea that if you have a definition where two things are the same, and you can only reason about them when they're the same, you can try to replace one of them with something that could be anything. So here, we're going to take all those recursive places and change them to some variable. And then later, we're going to fill them in with the expression inside itself. Basically, the path of modular software is to remove the equality assumptions from your constraints. So I defined this type-level fixed point operation, and now I've unfixed the expression type, replaced all the recursive parts of this variable. But now, when I use the fixed points on the signature, then I filled it in and made it recursive again, and it becomes isomorphic to what I had before. But while it's still in this unfixed form, then I can really do stuff. So say I wanted to break it apart or add new things. So here I've written it as a sum of products. It's a bunch of cases. Each case has a bunch of stuff. Well, I can break it apart by using a type-level sum explicitly. So I've broken it into the additive and multiplicative parts of the language. And define this type-level sum, which is just an OR. So I now stick the signatures together, and I have something isomorphic to what I had in the previous slide, except now I can work with the additive multiplicative parts separately. So in data types a la carte, it spends quite a while talking about various ways of dealing with these terms now that they're weird, you have all this indirection, and I'm not going to talk about most of that. I'm just going to give this big idea of a way of working with these. So back when it was all explicitly recursive, it was pretty simple. To write something that evaluates them, I just have a simple recursive function for to do an add. I evaluate the subterms and then add them. And so what do I do now if I'm using signature where I don't know what the recursive terms look like? There's this general idea that when you define something inductively, any operation you define or anything you prove has to kind of follow the same structure. So here I basically split the recursion and the cases into parts. So when I program over it, I'm going to have to do the pattern matching and the recursion separately. So first, the pattern matching. I'm going to use this funny type fint. That is, instead of filling in the recursive places with the sub-expressions, I'm going to pretend that someone else has already done the recursion and filled in those recursive holes with the result. And then once I have that, then it's very easy to compute the results for my layer. So for addition, someone has already told me what both sides of the plus evaluate to, and I can just add them. For constants, the same as it was before. Multiplication again. Someone has told me what both sides evaluate to, and now I just multiply them. And then at the sum, I just funnel things along. So now, how do I do this magic thing where someone else fills in the recursive parts? So I need some additional machinery. So this is a standard type class called functor. Basically, because I've marked all the recursive points with this type variable, I can now very mechanically find them and operate on them and change them to something else. So fmap takes a function and a term. It's basically going to apply all that function at all of the recursive points in that term. So this is fairly simple to define. The value is a base case, so it bottoms out there, nothing happens. Otherwise, at additional location, I just throw the function in on the subterms, and at the type level sum, I funnel things along. So now I can define my generic recursion operator. So what I've defined, I've defined that one-layer recursion a couple slides ago, and now I'm going to turn it into a general recursive operator. And how do I do that? This is called a catamorphism. So I start with a term. So I start with a term, and now I go to all the recursive points and use my entire recursive operation that I'm building on the subterms, and that map sends them there. And so now I have this sort of top-level signature where I replace all the recursive points with results, and I just use my one-layer operation right there. So in particular, if I do this on the eval function, I now have something that recursively evaluates terms. But I've defined my types in a modular fashion, so I can easily change this. So if I wanted to have a language that only had addition and no multiplication, all I do is I chop off this plus on the left here, and now I get difference code that does evaluation for the language that only has addition. And I haven't changed any other part of the operation itself, just at the end here where I'm kind of closing it off and seeing what it works on. So now, that was for this expression language where everything is an expression. How do I do this for a language with multiple sorts, where it can have expressions or declarations or other things? So I can do a similar idea, where now instead of having one type argument, I have two type arguments. So D is going to be filled in with the declaration type, and E with the expression type. So over in that decl F definition, where I want an expression in the assignment, I put E. Where I want a declaration, when I'm sequencing assignments together, I put a D. And now I define a new type level sum for things with two arguments. And now I want a fixed point for things with two arguments. So here I use the idea that I can use a fixed point operation to solve recursive equations in one variable. And I now have a system of recursive equations in two variables, so I can basically just put them in a pair and then use the thing. That
seems like type level records would really help here. So you could treat the pair of D and E as a single thing.
Yes, but you're still going to the problem that I'm building up to, which is, I don't think that solves the problem that you need one of these for every single RD. That if you then have 3 arguments, if you have 3 sorts instead of 2, you need another set of these. So you can do this by hand using these special things for every RD. Adam?
But with type level records, we could make this more extensible and assign a type to, for instance, add f that says it works for any grammar that includes at least x in decal, and the others can do whatever they want. That's actually a pretty straightforward thing to do with type level records and type theory, at least.
Okay. That is not the solution I have in this talk, but I want to hear more about that later.
Okay.
Instead, I'm going to use the idea from this paper from 2009. Generic programming with fixed points for mutually recursive data types. So let's look at the general form of these fixed point operators. So a fixed point for something that takes 1 argument is star, arrow, star, arrow, star. For 2 arguments, so I now have 2 of these different signatures. I now have 2 different signatures for each sort. Each of them takes 2 arguments, and I have 2 of these things overall. One for the things where the first sort is a top node, and the other for the second. So in general, my n argument fixed point is going to be, I'm going to have n things, the n sorts. They're n signature arguments, each of which takes n arguments for recursive points. And I can use this idea that a tuple of n types is the same. If I had a kind with exactly n elements, a tuple of n types is the same as a function from that kind to type. So, like a pair AB is the same as a function from 0 or 1 to the things that A can or B can be. So now I can use that and write this, expand this out, and rearrange the arguments. And I see that a general, this general n argument fixed point has kind n arrow star, arrow n arrow star, arrow n arrow star. That is, it's basically the same as my 1 argument fixed point, but now it's on these tuples of n. So I don't know about Adam's language, but in the languages that I've used, I don't have the kind n, or at least not easily. So, but I can get away with just using star arrow star instead of n arrow star. And so now I have this one generic fixed point operator that can deal with an arbitrary number of sorts. And so that is an idea used in this compositional data types paper. Yeah?
Something's disturbing here. It sounds like you have to bring parametricity or something. That the star kind is supposed to have inhabitants that can't be told apart through the usual kind of case analysis. Otherwise, polymorphism doesn't mean what you want it to mean. So how can you use that to represent n?
I'm not quite sure I understood that.
So the important property of the kind n is that you have a way of telling apart the different elements of it. You need some kind of case, you need to do a switch statement that takes in a type of kind n and gives you something different in each case, right?
Yeah.
Star doesn't have that property, and it's important for parametricity that star does not have that property.
Okay, so I don't quite understand all of that, but we'll see on the next slide that we need GADTs, which give these equality constraints, which I think breaks whatever you just said.
Okay. I'll think about it.
So this compositional data types paper is basically about lots of various things you can do if you have data types a la carte. But kind of as an aside, they presented what I think is actually the biggest idea, which is how to use this idea from the previous slide to lift data types a la carte into things with arbitrary number of sorts. So here, So we're back in the expression language. So here we define instead of using this type argument for the recursive points, we use a functor argument, where basically I pass in a sort, and it gives me terms of that sort. So now, for addition, I say, I take my magic recursive argument, and I ask it for an expression, I ask for another expression, and what I get is something created by the expression signature you sort as expression. And this may seem a little bit redundant, except now I sum things together, and so now I can have an expression or declaration of either the declaration or the expression sort. And so now I define this higher level fixed point thing, which basically looks a lot like my original fixed point thing, except now after I've filled in the recursive holes, I provide this extra label argument at the end. And basically what this looks like is that this is a type of labeled trees. And if every tree is labeled, every node is labeled with a sort of that term. And so a term, expression, or declaration with a decal label is a type of trees where the top node has that declaration label. And that is isomorphic to the declaration type that I defined by hand a few slides ago. And so once you have this, you can do a lot of cool stuff. So I'll show off a couple things. So say you want to add annotations to your trees. So like you want to annotate every node with a label. All I do is I change my signature with this annotation operator. So I can have expression or declaration annotated with int as my signature. I take the fixed point of that instead, and now I have labeled terms. Or if I want terms with holes, find context instead of normal terms, I just use a slightly different fixed point operator where I can stick holes in places. And also what this lets me do is I can now do things like I can write a function which takes a term in any language and gives me a term in that same language plus labels. And I can write, and I've simplified things a bit here, but in the actual compositional data types library, they've written a way where you can write something that works in either terms or contexts. And you can also, of course, write things that only work in terms and only work in contexts. And just random comments, if people want to understand this. These happen to be the free monad and the co-free co-monad of my signature. So that gives me this way. So that gives me this way of representing all kinds of terms where it can freely add cases, freely add operations. And so now I'll look at the operations themselves and tell you ways of building them up. So a few things I want when doing this. I want both genericity and specificity. So I want to be able to do things in a very generic way where I don't have to look at every case. But sometimes I do want to have to look at specific cases. And then I want the two sides of modularity, or reusability and robustness. I want to be able to take my fragments from the traversals and combine them in new ways. But also I want separation between the operation and the type, where say I can add if statements to my language and not have to change all my operations. And I want to do all of this while still having very good control over my traversals. So I'll show you a few of the common ways of doing this that you might be used to and things that don't work. So, of course, the first thing people do is what I call by hand. This is like our first evaluation function. We just write in all the casing, all the recursion explicitly. So this is something's going for it. It gives you a lot of control, and you're very good at special casing things. But it doesn't have any of the others. I can't take the multiplication case of that evaluation out and put it somewhere else. If I add a new sort, I will have to change this. That's not interesting here, but if your operation is like getting a list of all integer constants, I kind of like to be able to treat multiplication and addition the same and not case them both explicitly. So next thing a lot of people try is the visitor pattern. Basically, you write a few traversals, and then you just supply different callbacks. So now, it's basically the same as before, except you've totally given up control. In that you'll go through things in the exact order that your visitor pattern lets you. But on the other hand, if you want to add new things to your language, then you only need to update a few visitors and not every single operation. So some people look at this and say, well, what's an AST? It's like a node with a label and a bunch of children. Why can't we just use this uniform representation to do anything? So now you can do things somewhat generically, like you can treat addition and multiplication the same if all you want to do is look at the integer constants. But you've kind of given up your ability to use specific things. It's like, if you have different intermediate representations, maybe one has for loops, one has them compiled away. It's very easy to write something for one fragment and accidentally use it on a different fragment. And you're now even less robust than you were before, in that you might change your language and break your code, but it will still compile. So a big step in doing this, what are called recursion schemes. This here is a classic paper from 25 years ago on using recursion schemes. So I've already showed you a catamorphism earlier. That is the most basic example of a recursion scheme. So here is my catamorphic evaluation function again. And I'm not going to go into too many details, but basically you can do a lot more with catamorphisms. Like, so here you can only read from subterms. But if you want to pass things down as well as up, maybe I want to do type inference. So I want to pass down an environment and get back a type. So then instead of building up an integer at every level, I'm building up an end error type at every level. And then I can do this. Now, of course, you still have the problem that the catamorphism is forcing you to this kind of one-layer thing where you can only look at the top node and the results of its children. But luckily, there are 5 bajillion other recursion schemes that you can use. So pick a problem, pick a kind of recursion you want to do. You can probably find something on this list that does it, or if not, there are ways of generating new ones of these. It's like, if you want to build things up one layer at a time, you can use the anamorphism. If you want to build things up many layers at a time, you can use the futuremorphism. That's what I'll say about recursion schemes. But now you're starting to get a bit more. So we've seen how they can be specific and robust. You have a little bit of control because you can choose different recursion schemes to use. And because we're in this unfixed representation where you have a type argument at every recursive point, there are some generic things you can do there. And there are operations that will just combine things at every recursion point in certain ways. But you still can't really combine these in any interesting way. It's like you can combine things. It's like if I have an evaluation for the additive language, I can combine it with the evaluation for the multiplicative language. But that's about it. So now we're going to look at updatable fold algebras. And I guess the authors decided updatable fold algebras didn't sound cool enough. So the previous paper kind of created this convention of writing catamorphisms with banana brackets. So catamorphisms are called bananas, and if you have really big language, then you'll need to deal with some large bananas. So before, we had kind of been writing the parts for catamorphism separately. For just a moment, I'm going to pretend that we've all smashed them down into an explicit structure, like this. So once we've done that, it's now very easy to operate on the pieces of our catamorphism. So we can write things of type kata, arrow kata, and these transformations and kind of build them up. So as a simple example of this, I'll look at the crush updatable fold algebra. So it takes a monoid. It's a way of smashing values together, and recursively applies that over every node. So like an addition, I will take the results from crushing both subterms. I'll combine them with the monoid operation. So now, say I wanted to get a list of all integer constants in my program. I just change that. I just change the operation I do at values to return a singleton list, and then I turn that generically into a full recursive traversal, and now I have a one-liner that gives me a list of all integer constants in my program. And similarly, if I wanted to count the multiplications, I just add a 1 at every multiplication site and do the same thing with the integer monoid. And now I have something that counts all the multiplications in my program. So you can kind of kind of generalize this to all the other recursion schemes. And so now we're exactly where we were before, but now we're starting to get reusable. We're starting to be able to combine things in interesting ways, and correspondingly, we're now starting to be able to do cool things with one-liners. But strategic programming is what really takes us a lot further. I guess I'll beat up on Celio since he's not here, but this is what lets you take all the things that TXL has built in and just do them yourself in one-line code. So it came from this language called Stratego, which is a domain-specific language for doing program transformations. There's really this paper, The Essence of Strategic Programming, that really showed what it's all about and how to do it in logic programming and functional programming, and even object-oriented programming with visitor combinators. So the general setup is I had these fragments of traversals, these generic operations called strategies, and I went to combine them in certain ways. So there are a few big ideas that make this very powerful. So before, with my updatable fold algebras, in order to update pieces, I basically had to be able to look inside the catamorphism and see what the pieces are and then swap them out. But now I'm going to let things fail, and this is what's going to let me do updates without looking inside. So if I have something that only works on expressions and fails for non-expressions, and then something that only works on declarations and fails for non-declarations, and then something that works for everything else, I can easily combine them, saying, in something that tries the first, then tries the second, and then tries a generic operator. And that will work for everything and do specific things for expressions and declarations. And I can mix and match those in different ways and get different fragments. So these are some of the general combinators that you can use to do this. The big ones are that ad hoc combinator, which tries this type-specific operation if it can and else does something generic. And then there's that fail, and then I can case over failure. So I can try something. If it succeeds, I then do one thing. If it fails, I do another. This other big idea is building up my traversals from these one-layer traversals. So I have these guys all and one. If I have something that applies at one node, I can use all on it, and now I've listed something that applies on all children. Or I have one, which makes it apply in the first child where it succeeds. And so now I can build up a bunch of interesting other strategy combinators from this. So there's try, where it tries a strategy. If it succeeds, then good. If it fails, then it just leaves the term the same. And I can do traversals. So top-down, it does a strategy at the current node, and then at every child, it does a top-down traversal. And I can even do fixed-point stuff. So this is basically the idea of if you have something like, say, common sub-expression elimination, where doing it lets you do more things. You basically go down to the leaves and just do it until you can't do anything more, and then you go up and do some more stuff until you can't do anything more, and so on, until a fixed point is reached. So I'm going to defer the examples of how you actually use this for a few you can just basically see that there's a lot like updatable fold algebras, except now they're more updatable. You can combine them in more ways, and now I'm starting to get some control of my traversals again. But are they type safe? And that brings me to the last part of my talk. So I know of 3 previous attempts to bring strategic programming into functional programming. The big one is Stefanski, written by the strategic programming guys, which, by the way, I'm currently the maintainer for on Hackage. And then there's Reclib, and more recently there's Cure, the Kansas University rewriting engine, which is still under active development. And this is Haskell, so of course every library comes with a paper. And Cure actually had another paper out just last year on a new version. Basically, all of these work the same way. They use, even though we're in statically typed language, they use dynamic typing. So Reclib and Stefanski use data.data, which is this built-in Haskell thing where that lets you convert stuff into this dynamic any type. For Cure, you kind of have to write your own any type. It's like you write a G, which could be an expression or a declaration or anything else. Basically, all this is the problem that's like, you want something which takes declarations to declarations, but instead you get something which takes any to any. And so at every point when you're using these, you have to do a type case, and you have to have failure, and you basically can't write anything that's guaranteed to succeed, even if you know it should be guaranteed to succeed. So that's where I come in. So while I was working at my company, I wrote this library called Compstrats, and I finally released it just last week. The big idea is that these compositional data types, that I was talking about earlier, these are exactly the ingredients that we need in order to make this type safe. So if I want something that applies to any sort, but keeps the sort the same, I just say for all sorts, things of that sort to things of that sort with effects, which is what the monad means. And so now I can write things that are guaranteed to succeed. I just need one extra ingredient to do this. If I have something of some unknown sort L prime, I need to be able to check whether it's the sort that I want. And I implement this using equality types.
But then you use
Mhm.
you use a dynamic checking.
No,
process, which is
yes.
from the sorting you
So what this thing does behind the scenes is it inspects a top-level term, and from that it can get an inequality type. So like it can say this is a term of some unknown type L, but here's runtime evidence that L is equal to expression. And then once it has an equality type, it can do a cast safely.
But how is din proj not dynamic typing?
So that part is, it's in the name. That is dynamic typing. The thing is, the rewrite itself is not dynamically typed, in that I can prove my type signature that it keeps sorts the same. So now I'm going to use this, give an example of an operation that deletes a statement at a certain label that works for any language that has statements. So I start off with my basic delete prime, which is all it does is it takes a statement, throws it away, and gives you an empty statement. This is my bottom layer. I can then lift that using this target label combinator, which takes a rewrite and a label and gives you a new rewrite, which it will check if the term has that label, and if so, it does the rewrite, and else it fails. So now I have something that only applies as the thing of that label. And now in one line of code, I'm going to lift this into a traversal of my entire program. So I lifted something which only applies in Node if it has that label. Then I use this promote rewrite with failure combinator, so it applies, this now applies to any sorts, it just fails at all the non-statements. Whoops. And now I use my one bottom-up rewrites combinator. I lift this into a traversal of my entire program, which looks for the first place where it can do this, the first statement for that label, and it does the rewrites. And then finally I say, and if this fails, meaning there's nothing with that label, then I leave it the same. And so that's how, with just one line of code, I've turned this basic thing at the leaf into a traversal of my entire program. And because I'm using compositional data types, this works on any language that satisfies its constraints, which I haven't told you about, which will basically say something equivalent to this language has statements. So now things are more type safe, and so we have everything that's on this list. So limitations. So you might notice that I'm returning empty statements instead of actually removing the statements. This is a hard problem. I haven't really seen anyone solve this other than by doing everything by hand. I have some ideas though. More specific problems. So you do lose some type precision. So if you want to get the name of a type in a class in a Java file, every Java file has a class or an interface. So you know there's always a name. So it's in the type this should always succeed. But as you're writing this, you kind of go for this intermediate layer where it can like apply to anything that has declarations of that form. And by the time you go around saying, and now I'm going to only do this for Java, you still have lost the information that it always succeeds. So you have something that can fail even though it always succeeds. And then finally, now I'll tell you what those constraints are. You basically have parameterized everything out, and so you can get something pretty huge. So now I'd like to leave you with a thought as far as why this is so important. So here's a quote from Ralph Lemel again, written in the Y2K era. It's basically talking about all this heterogeneity out in the programming world and why that makes it so hard to write tools that can handle a lot of software. So he says you should take the 500 languages in the 500 language problem poetically. But language isn't the only thing that determines whether someone can use your tool. You should also take the language poetically. Like, you might not care about most of these 500 languages, but you still have the 10 language problem. You have the 100 language database pairing problem. You have the 500 framework problem, and the 5,000 problem. This is not just about things written for the mainstream languages, but not for the long tail. This is about all the things that don't get written, because if they were, they could only be used for a few things. So we're all here because we think there's a lot of value in PL technology. Earlier this month at the admin dinner, Simon was talking about how no company has really made it big in PL. And I think this is why. It's that you can only build something once in the market. You don't just get 100 times your tools, you get none. So as we use techniques like these and find more and more ways to automate problems in a day instead of a year, and not start from scratch every time we solve a new problem, then I think we're really going to see an explosion in what we can do. Thank you.